Hello students, welcome to this class, and this is an interesting topic, quite an easy topic to discuss, that is holography. Now in this lecture I will talk about the construction and reconstruction of a hologram, and later on in this video I will show you the effect of temporal and spatial coherence on holography. So let's start the lecture. So holography is a lensless two-step imaging process which can produce three-dimensional images. Holography, it is a lensless while a two-step imaging process which can produce three-dimensional images. Now in 1948, D. Gabor, he was the first who suggested holography. Now what is the difference between a hologram or a holography and photography? Now as we know that in a photography, the images what we get from a photography is actually records the intensity distribution of the particular scene, while in a hologram the intensity of the optical illumination or the optical illumination is recorded as well as the phase. So in ordinary photography, we record only the intensity of light and no information about phase. So it is not a three-dimensional characteristic, and hence the 3D characteristic of an object is actually lost in ordinary photography. But in holography, we records information regarding both the amplitude and the phase. The word hologram is actually derived from Greek word holos, and that holos meaning the whole or the entire, that is the whole or entire of information. So let's start how to construct a hologram. Now this is the recording procedure of a hologram. This is the hologram. Now a laser beam, if comes in this way, so this beam is known as the object beam. This is the object beam. This is the object. It is a semi-transparent mirror, and this is the laser beam. Okay. So this diagram shows how to record a hologram. Here a beam of coherent light. I will discuss later on why coherency is important for recording as well as the reconstruction of a hologram. But now a beam of coherent light from a laser source, this is the beam of a laser or the beam of a coherent source like a laser, it is splitted into two. It is splitted into two by a semi-transparent mirror. This is the semi-transparent mirror. It splits the incident laser beam into two such that one beam called the object beam, so this is the one that is known as the object beam, can be scattered by the object to be photographed. So this is the object for which we need the hologram. So object beam is scattered by the object itself, and the other beam, that is the phase related reference beam. This is the phase related reference beam. It falls directly on the film. Now this is the photographic plate in which the hologram is going to be recorded. So one beam is the object beam, which is scattered by the object itself and goes directly into the hologram, and the other beam and the other splitted beam, that is undeviated, it falls on the hologram, which actually records the phase relationship. So these two beams now form interference pattern on the photographic plate or on the hologram. The fine speckled pattern on the film thus contain informations regarding both the amplitude and phase. And hence, this is the process how we record a hologram. Any question about this? Is it okay? Is it clear to you all how a hologram is recorded? Okay, fine. So now once a hologram is recorded, we have to move on the mathematical analysis of the construction procedure. So that's why I'm omitting this one. Now let the complex amplitude of light wave scattered by the object and striking the hologram be A equals to A0 e to the power I k psi. This is the complex amplitude of light wave scattered by the object and striking the hologram. So this is actually the object beam. And now the reference wave be r equals to r0 e to the power e to the power I psi, and it will be I psi, and let it be phi. So let the reference beam be r equals to r0 e to the power I phi. Now as they are phase correlated, as they maintain coherency, so as they are phase related, the resultant complex amplitude, resultant amplitude be capital R equals to A plus small r. So A is the equation of an object wave. This is the object wave, and this is the reference beam. So the resultant amplitude will be capital R equals to small a small plus small r. Therefore, the intensity on the hologram, therefore the intensity on the hologram is capital I equals to capital R into complex conjugate of R, that is R star. So as R equals to A plus R, then R star should be A star plus R star. Putting the values and simplifying, we will get A star plus R star plus A R star plus R A star. Okay. Now A star and R star, it will give us A0 square and it will give us R0 square. Now what will be the value of AR star and RA star? Let's find out here. Now as A equals to A0 e to the power I psi, that means A star should be A0 e to the power minus of I psi, and as R is R0 e to the power I phi, so hence R star should be R0 e to the power minus I phi. I am omitting A0 star and R0 star as because A and A0 star or A0 and A0 star makes A0 square. So I am just putting A0 e to the power minus I psi and R star equals to R0 e to the power minus I phi. Now what will be the value of AR star? So AR star will be A0 e to the power I psi multiplied by R0 e to the power minus I phi. Okay. So this will be A0 R0 e to the power, taking minus I common, it will give us phi minus psi. And then find out the value of R A star or A star R. A star R will be A0 e to the power minus I psi into R0 e to the power I phi, or it will be A0 R0 e to the power I phi minus of psi. So these are the values of AR star and RA star or A star R. So putting the values of AR star and RA star, we will get A0 R0 e to the power minus I phi minus psi plus A0 R0 e to the power I phi minus of psi. Now taking A0 R0 from this third and fourth term, what we will get? We will get e to the power I phi minus psi plus e to the power minus I phi minus psi. So it can be written as cos term of, that is, we have found A0 square plus R0 square plus A0 R0. So cos of phi minus of psi. Cos of phi minus of psi, and 2 comes from this. Let it be equation 1. Okay. So here we can find that the intensity on the hologram is A0 square plus R0 square plus twice A0 R0 cos phi minus psi, as because e to the power I theta plus e to the power minus I theta gives us twice cos theta, as we know it. So equation 1, from equation 1 we can see that the intensity on the hologram or the resultant intensity is thus the sum of two intensities. These are the intensities, so it is actually the sum of two intensities, that is A0 square and R0 square, plus the interference term contains relative phase information. So this is the term which carries the phase information. So here, when the intensity or when we construct a hologram, this is the way that in the hologram or the intensity of the hologram, here we can find that there are three terms. The first two terms, that is A0 square and R0 square, these are the sum of two intensities. These are the two intensities. And the third term, that is twice A0 R0 cos phi minus psi, actually gives us the phase relation or the phase information. Okay, now this is the construction process. Is it okay? Just give me a feedback. Is it okay? So let's move on to the reconstruction procedure of hologram. At first, we will see the figure of reconstruction, that is the procedure of reconstruction of a hologram. So we have already find that how a hologram can be constructed. Now the second part, that is the reconstruction part, that is if the hologram is formed, then how we will get the information from a hologram. So this is the reconstruction procedure or the reconstruction process. So let's take, this is the constructed, or this is the hologram what we have formed. Now this wave is known as the reconstruction wave. This is the reconstruction wave. This is the real image. And if it is extended behind, then a virtual image is formed. So this is the virtual, and obviously it is a 3D image. So this is a real image. So this is the way we actually reconstruct a hologram. This is the reconstruction figure or schematic diagram, how we can reconstruct a hologram. So here the hologram, this is the hologram. This is the hologram, and this hologram is at first illuminated with coherent light, which is known as the reconstruction wave. So this is a coherent beam which is actually of the same wavelength as the original beam while recording or constructing the hologram. So this is the reconstruction wave, which is actually coherent, or which is actually of the same wavelength as the original beam. So here the hologram acts as a diffraction grating. Here the hologram acts as a diffraction grating which produces two sets of diffracted beams. One set forms a real image, this one forms a real image, and the other set forms a three-dimensional virtual image. Okay, so this is the reconstruction step, and this is actually the second step of hologram or holography. First step is obviously the recording of a hologram, and the second one is this. This is what we know as the reconstruction of a hologram. And while for reconstructing an hologram, what we need a reconstruction wave. Now, what is the reconstruction wave? Reconstruction wave is usually of the same wavelength as the original wave we have used while recording or while constructing the hologram. And this hologram here acts as a diffraction grating or a diffraction element which actually produces two sets of diffracted beams, in which one set forms a real image and the other set forms a virtual three-dimensional image of the object. So this is the diagram for reconstruction of a hologram. Okay? Any doubts? So let's see the mathematical analysis of reconstruction of hologram. So let's find out the mathematical analysis. Now, by a suitable development process, the amplitude transmittance of the hologram is adjusted to be proportional to capital I, that is the intensity. Now, if the original reference beam is used to illuminate the hologram. If the original reference beam is used to illuminate the hologram, then the complex amplitude of light just after passing the hologram will be capital A, that will be some constant K, it is the proportionality constant, into R into I, where K is a constant of proportionality. Now putting the values here, R into I, and the intensity is already what we have found in equation 1, that is while construction of the hologram. And if you multiply with small r with this value of I, you will find it will give us R0 square into A plus R plus A0 square R0 e to the power I phi plus A star R0 square A0 star R0 square e to the power twice I phi. It is our equation 2. So it is just a simple mathematics. We have multiplied small r. Small r means that is R0 e to the power I phi with the capital I found in equation 1. Now here again 3 terms arrived. What is the first term? That is R0 square into A plus R. Now this first term represents a wavefront whose complex amplitude is proportional to that of the original wave amplitude, that is A plus R. So here the first term actually gives us K into R0 square A plus R. K into R0 square into A plus R. So the first term represents a wavefront whose complex amplitude is proportional, as because the term K is present here. So it is proportional to that of the original wave amplitude A plus R, and gives rise to three-dimensional virtual image. So this first part or the first component gives us the 3D virtual image. Okay. So this is the term responsible for the three-dimensional virtual image. Now let's move on to the second term, that is A0 square R0 e to the power I phi. Now if the reference wave is strong, then you can find that A0 square by R0 square is actually very small than 1. If the reference beam is strong, that is the intensity of the reference beam is higher. If the reference beam is strong, then A0 square by R0 square should be very less than 1. Hence, we can neglect this term, that is the second term can be neglected. So this term can be neglected if the reference beam is strong enough. Now let's move on to the third term, that is A0 star R0 square e to the power twice I phi. Now for a reference wave whose phase and amplitude are always or are almost constant all over the hologram, for a reference wave whose phase and amplitude are almost constant for all over the hologram, the third term is proportional to the conjugate of the object wave amplitude. So this is proportional to the conjugate of the object wave amplitude. So this is proportional, the third term is proportional, it is proportional to the amplitude, it is proportional to the conjugate of the object wave amplitude. And actually this is the term which is responsible for the formation of real image, and it forms the real image. So in the reconstruction process, we have found that there is one real image and the other one is a three-dimensional virtual image. Now this first term, that is k into r0 square, a plus r, it gives us the three-dimensional virtual image, and the third term, that is a0 star r0 square e to the power twice I phi, which is actually proportional to the conjugate of the object wave amplitude, and it actually generates the real image. Okay. Clear? Mathematical derivation of what? Shubhajit? Which mathematical derivation you require? I have derived both of the construction and the reconstruction procedure. So which one? So actually these are the two questions, or in holography, these are the actual questions what can be asked for. That is, the one is the construction procedure. I have shown you how to construct a hologram in both physically and mathematically. And the second question can be given, that is the reconstruction procedure. I have also shown in a figure, that is how reconstruction procedure is done. And then okay, fine. So now let's move on to, that is the effect of coherence. So actually in holography, initially, that is in the year 1948, initially LED, that is light emitting diode, is used for hologram to record, but actually no optical source, as you know, that is no optical source is coherent in nature. After the advancement or the discovery of laser, actually laser here forms or laser here takes the important role in holography, as because, as you know, that laser is quite a coherent source. Now, as you know, there are two ways of, or two part of coherency. That is, one is the temporal coherence and the other is spatial coherence. I will discuss both the cases. That is the temporal coherence, that is the effect of temporal coherence in interference, as because while constructing the hologram, you find that the two beams, that is one, the scattered beam, after scattering from the object, it comes to the photographic plate or the holographic plate, and the other one, that is which is undeviated, unscattered, and these two beams are interference in the photographic plate and record the hologram. So interference is actually the physical effect behind the hologram recording. So we have taken laser as a coherent source. Now I will show you the two different effects, that is while taking a temporal coherent source, and the other one is if the source is spatially coherent, what will what are the effects on holography. Now I will show you in a diagram form, in a picture form. So first of all, I will take a coherent light which is actually temporally coherent. So is it okay? Is it visible? Here I take two waves with two different wavelengths. I'm using two different colors to distinguish. One is W1 and the other is W2. So actually W2 is the wave which has a longer wavelength. Now let's take this is as a double slit. This is the double slit. Okay. Now what will happen in the, if this is the observation plate, then here now of higher wavelength or is of longer wavelength, then the peak to peak distance, will be higher, or peak to peak distance is longer. And as W1 is of shorter wavelength, the peak to peak distance will be smaller. So here you can find that these are the two wavelengths or two waves. One is W1. So this is the interference pattern. Interference pattern for W2. That is, I've used the black pen. This is the double slit. This is the point source. This is the point source. And waves with different wavelengths, waves with different wavelengths. So different wavelengths, that is W1 and W2. Here W2 is the longer wavelength and W1 is the shorter wavelength. So now if these two waves, that is the wave, the interference pattern, and this is the interference pattern for W1. Okay, for W1. So now after superposition, what is the result? What we will find? We can find that here as the two beams W1 and W2 has the same peak here, or at the same point these two beams have a peak, so the resultant or the superposition wave is actually this one. So this is the result of the superposition result. Okay. So in this figure, what I am trying to show you, that here I have taken two waves of different wavelengths coming from a single point source or point object, that is S. Here the two waves which have different wavelengths, W1 and W2, and as you can find out that W2 is of longer wavelength than W1. Now, as because W2 has a longer wavelength, while the interference pattern, while forming the interference pattern, the peak to peak gap is longer for W2. Now, as the two waves interfere in the observation plate or observation plane, the superposition results in this manner. So we have a peak in this, and then the second order or the third order terms decreases very fast. So this is the effect of temporal coherence. Now, have you drawn it? Is it okay? So here we consider a point source. Again, I am repeating that here we consider a point source emitting waves of different wavelengths. Now for the wave W1, it will form an interference pattern on the observation plane. And for the second wave, that is W2, with a longer wavelength, the corresponding interference pattern will have a longer peak to peak distance. Now, as the two patterns are of different wavelengths, they will add up on the observation plane in intensity, forming a new pattern with an imposed envelope curve, so that the intensity of higher orders will decrease more quickly. So you can find out from the superposition or at the extreme end of this figure that the higher order of the maxima, they have decreased so very fast. Okay, so this is the effect of temporal coherence in holography. And let's move on to what will we have when spatial coherence, that is an optical source which have spatial coherence, then what will happen? So again, at first I will show you in figure what will happen, and then we will move on to discuss physical. Have you find it interesting, the topic of holography? I don't think all of you find it interesting, as because only 6 viewers are here and only 2 or 3 are responding. That is Shubhajit, Keshav, Ipshita. So Shangomitra, okay, Shangomitra. So have you find it interesting? Now again, I am taking, let it be S1. I am drawing the wavefront of S1 here. Later I will draw S2. So this is the double slit. This one is the observation plate. And we can find out that so this one is the interference pattern for S1. Okay. Now let's move on to the second source, that is if S2. Now this is S2. What is S2? S2 is actually the displaced point source, but it has the same wavelength as because it maintains spatial coherence. Okay, so this is the displaced point source S2, but which has got the same wavelength of S1. So this is the wavefront of S2, that is what I have shown in the blue color. So this is the interference pattern. This is the interference pattern for the source S2. Okay. Now here the superposition results in, now that is the resultant wave. This is the superposition wave. Superposition result. Now this is the superposition. So in spatial coherence, actually an extended light source, this is not a point source, this is actually an extended point source, extended light source. Extended light source consisting of two identical single wavelength light, consisting of two identical single wavelength light source, and they are separated spatially. Okay, here I have used the black color for S1 and the blue color for S2. So if we have a point source S1, then the light from it travels to a set of double slits where it will be separated into two new waves. It will separate it into two new waves. Now these two new waves will interfere each other and form an interference pattern at the observation plate. So for S1, this is the interference pattern which I have shown in the black color. So this is the interference pattern formed by the source S1. Now for another point source S2, as because this source containing these two point sources S1 and S2, so I am talking about an extended optical source. Okay, so for another point source S2, now of the same wavelength, which is actually slightly displaced from S1 with the same distance from the double slit, it will generate almost identical but shifted interference patterns on the observation plate. So here S2 source, actually this S2 is slightly deviated from S1, and that's why this optical source is an extended optical source, not a point source, but you can consider these S1 and S2 are 2-point sources of the same wavelength. Now, this S1 and S2 is obviously at a same distance from this double slit. Otherwise, it will not happen. So, these 2 points or these 2-point objects are actually from the same distance from the double slit. Now, these waves from S2, it will also interfere in the observation plate, and the observed values or the interference pattern here I am shown in the blue pen. Okay. Now, these two interference patterns will add up in amplitude and often result in a drop in the contrast of the superposed interference pattern in terms of intensity. So, in the first figure, while showing the interference pattern or the resultant for a temporal coherent object, what we have found that the superposition results in a resultant wave in which the higher order terms decreases very fast. But in this type, that is, while the sources are spatially coherent, while the sources are in spatial coherence, here you can find that the resultant superposition result, here the resultant part actually gives an interference pattern in terms of intensity, and here a drop of contrast is shown. So comparing the effects of spatial coherence and temporal coherence, what will we conclude? What will be the conclusion? That is, whether we have used or whether we must use a temporal coherent light source or a spatial coherent light source for holography. What will be our answer? So while comparing these two cases, that is the effects of spatial coherence and temporal coherence on the sharpness of reconstructed images showing in these two figures, we can see that spatial coherence directly changes the contrast of the interference pattern. Here, in spatial coherence, the contrast of the interference pattern has been changed, while in temporal coherence, reshapes it by imposing an envelope curve. That means the higher order terms have decreased so fast. So these two have ill effects on holography, but we have to use, and later on in this part of holography, as the subject extends or as the subject progresses, the procedure while taking this type of light sources or optical sources, we this is the simpler form of explanation, that is the construction procedure and reconstruction procedure. These are only the simplified form of how a construction of hologram and how a reconstruction procedure is done, but this is not the all of holography. But in this lecture or in this syllabus, while studying holography, this is all about holography. Okay? Have you any doubts? Have you any questions? Tell me. Or otherwise, I will end the broadcast. Is it okay? Any doubts from you? Okay, I have every day I'm telling you that I'm waiting for your feedback in the WhatsApp group of the second year MSc Physics, but no one is bothered to give me a feedback, as because the coordinator sir is there. So if some feedback is given from your side, it will be helpful or useful for us to consider that whether the classes are taken is quite useful for you or not. In previous diagram, there were no source. No, there is a source, that is S, but in temporal coherence, because in temporal coherence, that S is producing two different wavelengths, that is W1 and W2. But in spatial coherence, here as we are taking an extended object, so here I have shown two different sources, that is S1 and S2, as because the 2 point objects are extended, are made difference or distance between them to form an extended object. But in temporal coherence, only a point source is used. In the previous figure, that is in the first figure, that is while I am discussing about the effect of temporal coherence, I have shown S, that is only a point object from which two different wavelengths, or from which two different waves of having wavelengths W1 and W2 are produced. Okay. Hologram diagram, that is while construction or reconstruction of hologram. Sir, is there any mathematical derivation? Yes, I have already discussed two mathematical derivations, one for the construction and the other one is for the reconstruction. But no, for temporal and spatial coherence, this is only the effect. In your syllabus, it is given previously. That is the effect of coherence in holography. Okay, so there is no mathematical derivation for the effect of temporal and spatial coherence in holography. So these are the diagram, and from this diagram we actually explain what are the different effects of temporal and spatial coherence on holography. Okay. So let's conclude this lecture. Goodbye.